Another commonly used mixer circuit is a diode ring mixer. It uses diodes as circuit elements, so it's a passive switching mixer, unlike diode or FET mixing circuit, which are active mixer circuits. So it uses diode, so it's commonly referred to as a passive switching mixer circuit. Now you see these two configurations are equivalent. It looks like a bridge rectifier, full bridge rectifier. In the second configuration, you can see that the this P injection devices, the way they are connected, it's P to N, P to N. It's one and the same configuration with the local oscillator, the same node, the center tap transformer, the local oscillator. Current or signal is being applied at the center of this bridge circuit. These are essentially the same nodes. Now, how the mixing is done is you see if you have a center tap transformer which provides you with the local oscillator signal. When this is positive and this is negative and this is alternating, you see this again is positive, this is positive, and this is negative. Then the bottom pair, the bottom diode pair is on, and it conducts. So the current is conducting, is being conducted in this manner. Now, when this side is negative and this is positive, then you have the top pair that is conducting. The top pair is conducting in that cycle, the negative half cycle. So in one half cycle, you have the bottom pair. In the first half cycle, positive half cycle, you have the bottom pair that is conducting, and then in the negative half cycle, you have the top pair that is conducting. So what happens is that the voltage from the local oscillator transformer alternatively drives the top diode pair and the bottom pair into conduction. So the local oscillator signal it has to be made large enough. So it has to be made large enough so that the impedance or the resistance of the diode switches is small. I mean the local oscillator amplitude should be so that it can forward bias the PN junctions and it can turn the diodes on. And this conduction is being carried out at the local oscillator frequency, omega L again. Now you see that in this schematic, let's try to understand what's going on in this circuit. I have bifurcated the circuit. So this is my RF part. Okay, this is my RF part, and this is my local oscillator part. So this is local oscillator. So what happens is that if what we have seen previously, the node voltages V1 and V2 are basically phase inverted. They are phase inverted as we have seen previously. So this V2 is minus V1, it's minus V1, and V out over here is a combination, or it's the return path of both V2 signal and V1 signal. So this is V2 plus V1, and if you can guess this correctly, well, the output is 0 over here. So that's how the RF part is. Similarly, same thing is happening around here. So in the return path at the ground, over here you have 0. Okay, and similarly this V3, V4 are phase inverted. So V4 over here is minus V3. Okay, so basically the same center tap operation. You have two independent AC sources. You have two independent AC sources over here. Only the difference is the local oscillator frequency and the RF frequency. The local oscillator frequency is 100, RF is 10. So let's have a look. This is a dual tone harmonic balance simulation. Why harmonic balance? We use harmonic balance to simulate the nonlinear circuit elements. You see this diode is a nonlinear circuit element. Why it's a nonlinear? Because IV characteristics are exponential. So it's not a linear circuit element. This is the diode model. So let's have a look at the node voltages V1 and V2, the time domain voltages V3 and V4. So you see, as expected, we have right now we don't have any connections. So the current, the local oscillator current is not connected to V1. Similarly, V2 is not connected. So what we have is a bifurcated circuit. So what we are looking is two separate parts separately, RF part. So we have separated this RF and the local oscillator part over here. This is the local oscillator part. So we have separated these two parts. Now, you see, as expected, the V1 and V2 are phase inverted. Similarly, this V3 and V4 are phase inverted. This is high frequency. The frequency is 100 hertz, or it's 100 hertz here. So if you can guess, you see, well, you can also have a look at the magnitude spectrum. This is 0.1 kilohertz over here. So this is a single tone. All this both the magnitude of V3, V4, they're phase inverted, yes, but the frequency is the same. So one can expect the magnitude to be at 0.1 kilohertz. Similarly, this is a low frequency. This is at 0.01 kilohertz or 10 hertz. This is a 10 hertz signal. This is a 10 hertz signal, and so this is a 100 hertz signal. So this is a 100 hertz signal. So you see over here you have one cycle. This is 100 milliseconds is 0.1, so 0.1 versus 10. So similarly in 100 milliseconds you will have 10 cycles. This is 100 hertz. Now once you connect the local oscillator part with the RF part over here at the voltages V1 and V2, well, what happens is that you start mixing up the currents. So you mix the local oscillator current over here with the RF current, right? You mix this with the RF current. So what happens is that at the return path you will have a modulated output. You have a modulated output. Look over here. What happens? You see, once you start mixing the local oscillator with the RF, you start, this is V1 and this is V2, and as expected they're phase inverted. So V out over here, you see this V out is again V1. This V out, my V out is again V1 plus V2. So let's write this up. This is V1 plus V2, and you see that if you combine these two node voltages, you have an amplitude modulated signal, and this V in is just looks like writing, or it's the envelope of the signal, the output signal. So what you have done is combine the local oscillator and the RF signal at node voltages V1 and V2, and then on the return path you are getting the mixed products. That's the product of RF and the local oscillator currents, voltages. So you see that in the spectrum, as expected, the spectrum of 10 hertz, which was like this. This was your baseband signal. This is shifted at the carrier or the local oscillator frequency 100 hertz. So as expected, this is your 100. So you see the carrier or the local oscillator is suppressed. You don't have anything at 100. Well, you have the two sidebands at 90 and at 110. So this shows that you have mixed up the voltage signal, the RF and the local oscillator signals. Now, just to understand this situation further, suppose you have a square local oscillator of the same fundamental frequency, 100 hertz. Then, as discussed earlier, if you have a square local oscillator waveform, then multiplying a sinusoid, you can see this in the blue input, RF input, with a square results in a modulated output, which in transform domain translates to the shifts at the odd harmonic. So for example, this is 100 hertz, okay, this is 100, then this is 300, okay, with amplitude decreasing 1/3 of the sideband, and then you have 500, okay, this is 500, and then this continues. So you have 500, you have 7, this offsets the shifts at the offset, it continues, and the voltage is dropping. The voltages of the amplitude or the strengths of the tones that are shifted at the odd harmonics they are decreasing as expected in the Fourier series expansion.